Hi everyone, let's solve this problem. So basically, you can read the problem and understand it. I will casually discuss what the solution would be, what the idea for the solution would be. I'd solved this a bit long ago, like few months ago. I'll just discuss the idea, common idea, and further you can code it off based on the idea. So yeah, as the question says, they want the number of substrings which satisfies this condition. So what would be the brute force approach? They want total number of substrings satisfying that condition. How can we find it? One easiest way is to check if one substring, we can find whether a given substring will hold this condition. So we can do the same for all the substrings of the string, this string. So how can all substring be calculated? Basically, just make a nested for loop, like, and derive, like, and get all the substrings, and for each substring just check whether this condition holds. So deriving all the substrings will take n square time, and for checking whether this condition holds will take another n time, so it becomes n cube. So the brute force solution time complexity would be n cube. Now this can be a bit sub-optimized. So instead of you have a substring, instead of every time checking whether it holds true, you can pre-optimize the computation. So you can do some prefix or suffix maybe, but prefix would be enough. So prefix as like frequency counter for each of the characters. Each of the characters, by that I mean only the vowels. Consonant can be just counted as a common one letter. So just keep a counter and check if number of consonants is k as a like prefix prefix sum, and then check whether these are occurring at least once. Basically, the frequency of them should be greater than 0 in the given substring. So yeah, that will optimize the time complexity, and it will reduce down to n square, because each time you are checking in constant time. Next, let's think of optimizing this more. How can we optimize this more? So what we can do is we can basically use the concept of having k consonant in a subarray which we are considering. So we can like, by taking a hint of one of the condition, we can arrive at a solution. So they want exactly k consonants, not less, not more. So if they want exactly k consonants, we can think of a 2-pointer approach over here. So what I can do is basically, if this is my, so forget this. So if there is an array substring, like we will take basically 2 pointers, that is a left and a right pointer. So left pointer and right pointer. Right pointer will for each step, right pointer will move one position forward, that is rp plus equals 1, and left pointer will lazily move forward only if the number of consonants within the range of lp and rp inclusive is exceeding k. So lp will be if number of consonants, whatever is the spelling, in this range lp and rp is exceeding k, then do this. And yeah, and we are for sure that number of consonants will exceed only by 1, because let's say you're taking a subarray. Like initially you will start with rp and lp at the initial positions, right? So you can keep lp as -1, rp as 0, where 0 is the starting position. LP would be okay, you can just keep it as 0. So like initially there will be no consonant, so gradually it will come to K, and when it exceeds K, it is exceeding K only because RP has moved one position forward, so number of consonant is only at max possible to increase by 1. That's why if condition and not while condition over here. Yeah, so yeah, number of consonants can be again computed via prefix sum array, frequency sum array. So that will give you in constant time. So yeah, so if like let's say an image, I'll not write a proper code over here, but let's say there is a for loop over here. So each time in the for loop, you are incrementing the right pointer in like this rp plus plus, and now you're increasing the frequency of the new char which is present at rp. So s of where s is a string, rp plus plus. So now after doing this, you're checking if the array substring from LP to RP is valid, and that can be done in constant time again by keeping track of frequencies. So if it is valid, then you can further take a next step. So you know now LP to RP of the substring is valid. Now my whole aim in one current iteration is how many substrings are ending with the last character as at the position RP and are valid substrings. So now for this, you know, RP is fixed now. Now only way we can count is moving LP to back and forth. It can't move left side, because if it moves then it will violate, because we are lazily incrementing this, lazily moving this right to only when we need it, basically only when the frequency exceeds K. So the thing is, you need to find how far this can go right and still be the valid substring altogether from LP to RP. So this can be done via binary search, and you will still get optimal solution of n log n, because RP is incremented, like RP is traversing from 0 to n, and that's like a one pass, and for each pass you're just going to make a binary search over L with keeping low as LP and high as RP minus 1 or something. RP is enough, but yeah, and your made like whatever the binary search index you get, you will get something which is like, let me say that index is this, and it will be something like let's take some index, let's say this is the index itself. Now this index will be always greater than LP. Now you need to find how many substrings are ending with RP as the last position. That would be basically all the substrings which are occurring between index and LP, right? So yeah, so like basically if it's inclusive, then do just +1, then just add this to your answer. So this will be your all the substrings which are ending at RP and are valid. So binary search condition, you can just add it of whatever is the valid condition. That will be again taking a constant time, as we do pre-computation using prefix frequency array. Yeah, so what's the complexity of this? As said, it's n log n. Now what can we do? How can we optimize this more? So we have we have LP and RP, where RP is ending, LP is beginning. What we need to find efficiently is what can be the LP dash. What I mean is how far LP can move right. Basically after doing this, we won't move LP right, okay, in this approach. We just keep iterating forward, and LP will be the same way. It will only move when this condition holds. So yeah, coming back here, so what we are essentially trying to find is how far LP can move towards right, keeping the condition on hold, like key consonants are there exactly and these are occurring at least once. So it can only move forward till it encounters a consonant. Why? Let's take an example. Where is that example? Let's say I am over somewhere over here. I can say, where can I see? Let me say I am over here. So let me say I'm at the position A. Now where RP is pointing to A. Now I need to L will be almost around it, and the K value over here is 2. L will be almost around A again. LP would be pointing over A. RP would be pointing towards A. Why LP would be pointing towards A? Because if LP would be pointing somewhere at C or E, then total number of consonants will be greater than 2. So LP will be pointing at A now, and RP is pointing at A. So we need to find how far LP can go forward. So let me just see if LP is pointing at A right now, as my cursor suggests. So if it moves forward, is it still valid? Yes, A is there in this. Let me add over another consonant over here. Let's name it as T. Let's make it bolder. Yeah. So if let's say if this many elements are there, like these are the consonants. Now if you try to move forward, like if you might try to move LP outside, like exclude T, then there will be less than K consonants. So in that case you can't move forward when you approach a consonant. So you can only move forward till you face vowels over the path, and noting that the vowel frequency for each of the vowel will be at least one. So keeping track of that, you can just move forward. Now how can you move forward? So what you can do is you can just keep a track of frequency of vowels, and you can basically check how far at the leftmost position would be my vowel satisfying, like substring would be satisfying this frequency. And also that you can keep track of, while iterating over in this follow, you can keep track of what's the oldest consonant I have seen, at what position it is. So like let me say you found out the optimized index one, where you can move, like the number of vowels in the substring would be holding true, that each and every substring vowel is there at least once. Let me say that is an index 1, it will be greater than LP. And let me say there's another index 2 where you encountered a consonant. Basically that would be your hard stop over there. So what you can do is both conditions should be satisfied. So what you can do is you just take min of this and index 2, and what would be this? This would be your LP dash. How can I represent dash? Yeah. So this will be a LP dash, and the number of substrings ending at RP and satisfying the condition is LP dash minus LP plus 1. And now keep on doing this for your entire array, and then your answer would be solved, like your problem will be solved. Yeah, so this is basically it. And what is the time velocity for this? Since everything is happening in the constant time, and iterating the array once, so that will be linear. Thank you guys. I hope you got idea. It may be not complete, but you can proceed further for solving, applying your own logic over here. Thanks.